Hi everyone, happy Friday. It's 3:10, so we're gonna get started here. We are so excited to have Dr. Derya Akkaynak here with us today. She is an engineer and oceanographer whose research focuses on problems of imaging and vision underwater. She has professional, technical, and scientific diving certifications and has conducted underwater fieldwork from the Bering Sea to Antarctica. Akkaynak is an honoree for the 2019 Blavatnik Awards for Young Scientists in Physics and Engineering for her postdoctoral research, resolving a fundamental problem in underwater computing vision, the reconstruction of lost colors and contrast, which lead to the development of the Sea-thru algorithm. She currently works at Harbor Branch Oceanographic Institute in Fort Pierce, Florida, USA. So everyone, if you could please hold your questions until the end, we would appreciate it. You may enter them in the chat if you want throughout the presentation, but we'll get to them at the end. And thank you, Dr. Akkaynak, for joining us today. And you can share your screen and begin your presentation.
Nicole, thank you so much. And Coral, thank you so much, you guys, for reaching out and arranging this presentation. I am very excited to not physically be in New Hampshire in this weather, but to be talking to you. Can you guys see my screen okay?
Yep.
Okay, excellent. So I will go ahead and get started because I have a full seminar, and actually I'll stay half an hour longer afterwards to take all the questions that you guys possibly have. So please join me in exploring why there are colors in the ocean. Here is how I arranged the talk for today. Excuse me. I will give a very brief introduction about myself and my background, and then I will show you a little bit about some vision projects that I am not going to be talking about today. These are going to be visual ecology projects. Then I will go into the core of my talk, which is going to explore why there are colors in the ocean. What do colors mean? Can they give us scientific insights? And why is consistent imaging of colors underwater such a difficult and still an unsolved problem? Then I will move on to share my contributions towards solving this problem. And we'll go on to discuss what the future brings when we can consistently image colors underwater. So that being said, a very short introduction about myself. I was born and raised in Turkey, and by training, I am an aerospace engineer. After graduating with my bachelor's, first in my class, I got a scholarship to do a master's at MIT, also in aerospace engineering. And after that, as it commonly happens to young graduates in the US, I started working for a consulting company that was doing work in the field of IT, so information technology. I worked as a consultant in the US for 3 years. I was in my 20s. I made a ton of money. I traveled a lot. I had 1 billion hotel points and airline miles. And at some point, I realized that I was working so much that I was missing the changing of the seasons year after year. And at some point, I stopped and I asked myself, what kind of a job would I look forward to showing up to every morning? What kind of a job would make me feel whole and excited every day? And the answer to that was a job that puts the ocean in my life every day. So at that point, I left my high-paying consulting job and started a PhD in oceanography together with mechanical engineering, because my background's in aerospace, at MIT and Woods Hole Joint Program. I graduated in 2014 and never looked back. I did a bunch of postdocs, short projects after that. I worked in Panama, I worked in Israel, Germany, and the US. And most recently, I am a scientist at Harbor Branch Oceanographic, which is in Fort Pierce, Florida. Now, of course, Florida does not need an introduction to New Hampshire folks, because we have a consistent population of migrating snowbirds from New Hampshire every year. But I just thought I'd say a few words. These manatees you see here are actually on my campus. We have a channel that's coming into the campus from a lagoon from the Atlantic Ocean, connected to the Atlantic Ocean. And the lagoon is shallow. So when it's cold outside, the channel fills with manatees, 40, 50 of them at a time. So when you just eat your lunch outside, you get to watch and count manatees, which doesn't suck. And the first week I moved to Florida, I think I immediately became a Floridian because as I was walking on the beach, I found a package. Everything I read online said when you find a package in Florida on the beach, it has to be cocaine. So I was really excited. I immediately called the police. The police came. We took all kinds of precautions, wearing masks and gloves and preparing ourselves for the worst. And he opened the package, which just turned out to be 16 pounds of seawater soaked marijuana. So that was kind of disappointing because I was expecting cocaine, but nevertheless, I feel like a true Floridian, even though I moved here only a year ago. So if you can get your vaccine and have time, please come visit us in Florida. So since I changed careers and I became an oceanographer, my desire to put the ocean in my life every day actually came true. And in the last decade or so that I have been an oceanographer or oceanographer in training, I had the privilege of working in many remote and pristine and sometimes not so pristine places around the world. So I am extremely happy with the decision to leave a high-paying job in the tech industry and going back to academia to pursue a career in academia. But of course, coming from such a weird background makes my research also rather non-standard and very interdisciplinary. Most often, I find myself working at the intersection of ocean optics, computer vision, and visual ecology, and sort of acting like a bridge between these different angles, trying to translate one from the other and making everybody work together. And of course, by working in ocean optics, that also means indirectly that I am working in ocean biogeochemistry. So first, what I want to do is take just 5 minutes and tell you about two of my projects, visual ecology projects, that I'm not going to mention in detail today. These are about cuttlefish camouflage and color vision adaptations of sea turtles. I'm going to start with my most favorite video ever. This was taken by my PhD advisor, Dr. Roger Hainlin. He's at the MBL in Woods Hole. Maybe some of you know him, maybe some of you worked with him. I'm sure many of you have seen this video because it has been viral since he took it in the Grand Cayman in 2005. So I'm gonna play it now. Just keep staring at the rock as the camera is approaching to the rock. And soon enough, you notice that the rock is not a rock, but it is an octopus. Of course, the octopus are masters of camouflage, and they have incredible skill to fool our eyes and the eyes of their predators. So the video will now play in reverse one more second. Just look at the spot between the eyes. That's where the coloration begins, and then it spreads all the way to the skin. And when the camouflage is there, you see that it is not just a match of color. It is not just a match of pattern. It's not a match of texture, but it's everything together at the same time, even changing the dimensionality of its skin from 2D to 3D. This is absolutely mind-blowing. The fact that they can do this in a matter of milliseconds is mind-blowing, but perhaps anyway, to me, what's more impressive is that they can do this as colorblind animals. And by colorblind, I mean that in their eyes, there is no hardware. to discriminate colors. They could be sensing color a different way. We don't know that yet. We have some theories, but in their eyes, they can only sense one pigment. So they see everything as different intensities of essentially. So of course, I've been working with octopus and their cousins, cuttlefish and squid in the lab and in the wild for about 10 years now. This was my PhD project, still going on. And I have been putting them into, these are cuttlefish you see in these little circular backgrounds. I've been putting these animals, which are rather easy to work with in the lab, against different backgrounds. The examples you see here, the checkerboard, the sine wave, the cow pattern, none of these are natural backgrounds, of course. The cuttlefish would never experience them in the wild, but they are backgrounds whose statistics I know. And from the moment that I put them in the arena, I time-lapse them. The goal here is to see the decisions they're making until from the time they are presented with a new background to the time they show a stable camouflage pattern and don't move. And the one on the sine wave in this experiment actually never found peace and never settled. So this experiment resulted in a massive 4 terabyte database of time-lapsed cuttlefish. I'm still analyzing them. I wish I could tell you some results, but it's still in the works. So hopefully when there is an update, you'll hear about it. Another project I wanted to tell you about is the color vision adaptations of sea turtles. Now, this is very interesting because we, as humans, we are trichromatic. That means our visual system has sensitivity to 3 parts of the electromagnetic spectrum, which correspond to what we call red, green, and blue. Turtles, on the other hand, are tetrachromatic. So they have 1 extra photoreceptor, and that's actually sensitive to ultraviolet, which is really cool. They can sense signals in ultraviolet together with red, green, and blue. However, on top of their tetrachromacy, they have another adaptation for what we think is for better color vision in the water, and that's oil droplets. So here is the cone photoreceptors of a turtle retina, and this is an oil droplet. It's essentially a spherical micro lens that is filled with a substance that, depending on its concentration, changes its wavelength sensitivity, and it then changes how it filters the incoming light. And the retina, if you look at the retina of a turtle, these colored oil droplets are scattered all throughout like this. Now, this is very curious because only fish, birds, and turtles have evolved and retained oil droplets. In birds, people think that their role is to enhance color discrimination, which makes a lot of sense because birds themselves are very colorful. They live in colorful habitats, and they live on land habitats where light is broadband most of the time. Yet for turtles, the story is a bit different because, with all due respect, turtles are not colorful. And the habitats, the underwater habitats they live in, get progressively less colorful with depth or with viewing distance. So what is the role of these oil droplets for turtles who themselves are dull and they live in dull and duller environments? So we can't answer this question if we use cameras that are designed for the human visual system, which is essentially every camera out there you can buy off the shelf. So we built, together with my lab in Israel, actually, I'll talk about them at the end of my presentation, but Tali Trebich Marine Imaging Lab in the University of Haifa in Israel, we built a hyperspectral camera that has a 16-channel sensor, so it's sensitive to 16 parts of the electromagnetic spectrum rather than just red, green, and blue. sorry. That way, we are not capturing an image, we are capturing a data cube, and then we take that data cube and then we can parse it relative to the visual system of a sea turtle, which is tetrachromatic and has different sensitivities than ours. So here's the camera doing its first dive. Everything about it was built from scratch, including the housing in Tali's lab. And here it's doing its first dive. That's cool, but the actual cool part is the imagery we get from the camera. So that's what I'm going to show you next. On the left, you have the hyperspectral imagery analyzed according to the visual system of a real turtle, which has oil droplets. And what you're seeing in the imagery is a real turtle that we filmed in the Solomon Islands. On the right, you have the same imagery analyzed from the point of view of a hypothetical turtle, which has the same cones, same properties in the retina, except no oil droplets. So you see the effect of the oil droplets separating out the placement of photoreceptors, separating them out in wavelength axis, and therefore allowing for more colors to be discriminated. This is not how we think exactly turtles see, but this is how the incoming light is processed because of the presence of oil droplets. So the next steps would be to do behavioral experiments with turtles to confirm that this is actually how they see. So this is still ongoing work that I'm doing that's in progress. Okay, that took more than 5 minutes, but you get the idea. That's the visual ecology part of my work, which then connects to working with sensors and cameras and image formation models. And actually that brings me to the core of what I want to talk about today. Why are there colors in the ocean? What do they mean? And why is it so darn hard to image colors underwater? So the answer is, there are colors in the water because they tell us something. And yes, they can give us scientific insights. So it's very interesting that starting from late 1800s, sailors, scientists tried many different ways to capture and quantify the color of the water around them. And you can imagine the scale of the global ocean. You can imagine trying to do this by taking samples from one part of the ocean and then having to go to another part and just never being able to sufficiently sample the ocean from a vessel. We have this problem also today, not just 1800s. But eventually it was understood that the color of the ocean water tells us about what's in the water. If the water contains very little organic or inorganic material, it's more likely to look blue. And as the amount of, let's say, plankton inside increases, the color is likely to be more green. So very quickly and very deterministically, the color of the water definitely gives us scientific insights about what's in the water. But that scientific insight really became possible when we were able to start sensing the global ocean from space. When we could do that and put the entire color of the ocean water on a map, then we were able to derive those insights. And what I'm showing you here is a map from 1989. And this was the first time we were able to make sense of what the ocean color means from when sensed from space. And it took about 10 years to pull this map together and present the data. What the colors show here is actually the concentration of phytoplankton. Purple is higher, I believe, and red is lower. Every color coding can change everywhere, but what it represents is the concentration of plankton in the water. This took 10 years to make, but of course today we are able to do this on a daily basis using very advanced satellites and instruments on these satellites. And this as I'm sure many of you working in remote sensing or using data from remote sensing is aware, has absolutely revolutionized oceanography as we know it. Because if you think back to 1800s and people trying to sample the ocean water from vessels, and if you look at the scale of the changes of things we observe in the water, you can get a better sense that it would have been never possible to get these insights from sampling from ships. And what was happening was scientists or sailors were sampling at 2 different stations. And then they were assuming everything in between varied smoothly. But now we know there are very few things that vary smoothly in the ocean. There are eddies, currents, jets, rings, all kinds of dynamic activities going on that change from short time scales to very long time scales, from small spatial scales to very large spatial scales. So the color of the ocean water, the ability to sense it and interpret it, really revolutionized oceanography. Just to sum everything up, here's a beautiful simulation again of the concentration of phytoplankton. This one is done over time in different parts of the world. It's a simulation, and purple means higher concentration. And to be able to sense this and model it, we are able to estimate the concentration of phytoplankton. And of course, phytoplankton means photosynthesis. And photosynthesis, of course, means food for everything else in the ocean to eat, but it also means carbon. So the ability to quantify reliably the color of the global ocean gives us incredible insights about the role of the ocean in our planet's climate. So colors are extremely important. However, some people, including me, would argue that the fact that the ocean water has color is a huge problem, because I don't care what's in the water. I want to understand what's inside the water and what the colors of those things are and what they mean, and how to put that on a world map. So for someone like me, ocean color is a fundamental problem that we have to deal with. And just to clarify, I'm going to tell you now what I mean when I say color, because color is a subjective term that was defined originally for the human visual system. It's a sensation that's unique to everybody. So in a scientific context, especially in exact sciences, what are we talking about when we say color? For the rest of my talk, when I say color, I am going to be talking about the interaction between the reflectance of a surface. Now, reflectance is a physical property that says how much of a given wavelength that surface reflects or does not reflect. It's a function of wavelength, which is lambda. And the reflectance is a property of the surface. It does not change with anything else. So color then is the interaction of reflectance with the ambient light, whatever the ambient light is, denoted here by E, and ambient light, of course, is also a function of wavelength as well. Together, that interaction sensed according to an observer, according to a sensor. This is the key part. When we say color, we are not talking about an objective quantity. Color is always relative. It's relative to who is observing, to the sensor. But I'm going to simplify just for my talk and assume that everything I say from here on is going to be using a sensor that responds ideally to each wavelength. In other words, the sensor captures the intensities in each wavelength equally, and that capture efficiency is perfect, 100%. So I'm going to kick out sensor from the color description only for this talk and make it even simpler. So now what we have left when I'm saying color is that we have reflectance, which is again a physical property, and we have the ambient light. So in the ocean, the ambient light is the color of the ocean water. So as I say to you, I want to know the true colors of everything in the ocean. The rest of this talk, I'm going to say that a number of times. What I really mean is I want to see the reflectance of everything in the ocean corrected for the variations in the ocean water color according to a certain sensor. So it's important because color does not mean we are imaging reflectance. It means we are imaging reflectance as an RGB sensor, for example, an ordinary camera sensed it. I'm sure many of you are familiar with this definition if you work in physics, in optics. If you don't, it may be confusing, and it has been for folks in the past. So I thought it's worth it to spend a couple minutes just going over this description. So please keep in mind, color is a relative sensation relative to who's observing and what the ambient light looks like. All that being said, now I want to explain very briefly how an image is formed in the ocean. It's actually exactly the way how an image is formed in air, but there are some differences that I will get to later. We have a diver, and the diver wants to photograph this octopus. The image his camera will capture will actually be the superposition of 3 different images on top of each other. The first image will be the direct signal. That's the light that comes from the sun, hits the skin of the octopus, and reflects directly to the diver's camera without changing its direction, taking the shortest path. This is what we call the direct signal, and this is the signal that diver wants to maximize to get a good photo of the scene. However, because we are in water, and water is a heavily scattering medium, what's going to happen is some of the light that reach the skin of the octopus will reflect back, and then they will encounter some particles in the water. Here I show very exaggerated plankton. And that light that left the skin of the octopus is going to scatter towards the camera after hitting some substances in the water column, some plankton. And that's the signal I'm showing with the yellow arrows. This is also a photo of the scene, but it's a weaker and blurry version of the scene. It's kind of degrading to the image that diver intended to take. But that's not really bad. We can deal with that. What's worse is the signal I'm showing here with the red arrows. What is this? It's the light from the sun that enters the water column, but it's light that never reaches the skin of the octopus. It's light that just reflects, scatters from particles suspended in the water column directly to the diver's camera. So they carry no information about the scene whatsoever. And this is actually the biggest cause, the biggest degradation to underwater images that we deal with. So just to put everything into context, the image that the camera captures is going to be called I sub C, and C here means color channel. For the majority of the underwater imaging work we do, we use RGB cameras. So C means red, green, or blue for each color channel. This image will be the sum of the direct signal, which is DC. It will be the sum of the backscatter, which is that occluding layer of fog, which has no information about the scene. And there is the forward scatter, which I'm going to neglect for the rest of my talk today because it's really tiny compared to the other 2 signals. No need to make things more complicated with that. So this is how an image is formed underwater. And after this simplistic equation, I want to show you visually what the direct signal looks like and what the backscattered signal looks like. So here's the same diver. This time he's on the bottom right of the scene. and he wants to take a photo of the color chart that's right above the starfish. Color charts, of course, are tools we frequently use in imaging and photography. They are specially manufactured surface whose surface properties are known. So we know the properties of each color patch on a color chart. So when some change happens, like you take them underwater or you change the distance you image them from, we are able to relate that to the original numbers. So color charts are very useful tools. In this simulation, where the diver is on the bottom right, he's just too far. The image he takes will not contain any information about the color chart. Instead, it will be dominated by BC, the backscattered signal, which is that layer of occluding fog, which has no information about the scene, it's just water. So when he's so far from the scene, the direct signal is 0, backscatter is maximum, and the image essentially equals backscatter. There's no information. Once the diver gets a little bit closer, now the image that forms in his camera is going to start showing some hints of the actual scene of the color chart, because backscatter will reduce by a bit and the direct signal will increase by a bit. So he will have an image of the color chart, but the colors will be very attenuated and there will still be a layer of fog, but we will be able to see through this fog. Finally, when the diver is really up close to the color chart, the image he takes is going to be of the highest quality. It will contain maximal direct signal, so maximal signal of the color chart, and minimal signal of the backscattering, because the distance between the camera and the chart was small. The scattering from particles towards the camera was not so significant. And just to show you everything in context, if we had done it for a number of distances, here is what backscatter and direct signal would look like. And it's worth noting, both of them change exponentially with distance. So if you're an underwater photographer and you want to take better photos, the key to that is getting as close to your scene, as close to your subjects as possible. Now that we've looked at this visually, I want to show you the more detailed equation that describes this phenomenon. This was the image formation model that was being used for the last 30 years in the field, and why I use past tense, I'm going to get to it. There's no need to remember this equation. It's the same thing we were just looking at. On the left is the image, which has attenuated colors and a layer of fog. On the right is the direct signal plus the backscattered signal, which has no information about the scene. And JC in the direct signal is the most valuable part. This is the unattenuated signal. This is the scene we would like to recover. No need to remember this equation, just please pay attention to one detail. Both terms, both the D term and the B term, contain a parameter called beta, beta sub c. This is what's called the attenuation coefficient. And what I would like for you to remember is that both the D term and the B term have the same beta. Okay? Now let's move forward. Before we move forward, the color description I gave to you a couple of slides ago is the exact definition of JC. So if you're somebody who works with imaging in air, you ever only deal with JC. But if you are working underwater, your job is made much more complicated with all the multiplicative and additive terms that modify JC. Okay, so underwater color is a lot harder problem than color in air. Just to summarize, the problem that I work on and everybody else in the field of color reconstruction works on is the following. Given IC, which is an image with attenuated colors consisting of some level of fog, can we recover JC, the image without unattenuated colors and without fog? And the answer is not so good. I want to now show you the 3 most common ways color reconstruction fails. Okay, here's a scene, a real scene underwater with 5 color charts placed at increasing distances from the camera. I hope you're able to see the 5th one. There are 5 color charts at known distances. The first method of failure is that the algorithms that try to reconstruct the colors do not actually reconstruct the colors, they just change the colors. So in this result, the colors are still off, they are still hard to see, and they are not quote unquote accurate. They just changed. In the second most common way, the algorithms do an excellent job of removing that occluding layer of fog. So now if you look at the 5th color chart, you can see all the way to it much more clearly, but you will notice that the colors are distorted. So at the expense of increasing visibility, algorithms lose accuracy in color reconstruction. The third most common way of failure is the pixels that are close to the camera get corrected beautifully and as close to the ground truth as they can be, but pixels further and further away from the camera get overcompensated. And that generally happens with overcompensation of red colors because that was the color that was lost most quickly in the water. So in this failed correction, if you look at the between the 2nd and the 3rd color chart, there is a red halo that goes all across, and it actually gets worse as you go farther from the camera. So these are the 3 most common ways color reconstruction algorithms fail. So why is this happening? Given that this is 2021 now, why have we not solved this problem of color reconstruction? And the answer is because the equation that I showed you and said there's no need to remember is actually an equation that was derived for the atmosphere. Now, let's think about how light attenuates in the atmosphere versus in the water. On the left, I have a photo of a pumpkin patch. The orange objects are pumpkins and they are under fog. And on the right, I have my friend trying to take an underwater measurement roughly 1 meter away from me. So when you look at these 2 situations, 2 things are immediately clear. First of all, there is no color cast in the pumpkin patch. Yes, there is fog. Yes, the visibility is reduced, but things still have their color and the fog is more or less white or gray. Whereas underwater, there's always that signature blue or green color cast. Of course it's there because water, even if there's nothing in the water itself absorbs. And it does so in a wavelength dependent manner. So some wavelengths, in this case reds, get attenuated much sooner than others. This is a major difference. On land, in the atmosphere, it's very rare in extreme cases that you see a wavelength dependent absorption. For example, after wildfires or a colored dust storm, that may happen. But 99% of the time, fog or haze attenuates independent of wavelength. The second difference is in the pumpkin patch, we can still see few tens of meters into the scene. And even on a very foggy day, you could potentially see 100, 200 meters ahead of you. So the scale at which the attenuation takes place is much larger, whereas underwater, in this case with my friend, we are tied to each other so we don't lose each other in 1 meter of distance. So the distances over which we lose visibility are incredibly small. So just by thinking about these fundamental differences, we should have known that a solution that mathematics describing the physics for light movement in air were not going to work for scenes underwater. But how did it happen that our field for the last 20-something years were using an equation from the atmosphere to correct images in the water? To answer that, I'm going to take you back 200 years, okay? 1826, that's when the first photograph, as we know photographs, was made. Not so long after, only 30 years after, the first underwater photograph was made. And that's not by immersing a camera, but rather the camera being in a protected box that was lowered into the water. Early in 1910s, we were able to measure the spectrum of daylight sunlight down to 600 meters depth. That's quite remarkable. Following that, and after World War I, we figured out the physics and the requirements of better visibility in the atmosphere. After World War II, we started to focus on better visibility in the water. So of course, these wartime developments that were not public at the time then became scientific and public knowledge, and were taken on most notably by Duntley's Visibility Lab, which started at MIT in the 30s, but then moved to Scripps. In the 60s, we have the first underwater camera that you can immerse into the water. And Duntley actually publishes his seminal paper called Light in the Sea, which we still use and cite today, that lays out the fundamentals of vision and visibility in the water. 1975, first digital camera is invented. And just about that time, still when we don't have fast computers, the first computer simulation of underwater scenes is done again in the Visibility Lab by Ben McGlamery. So this is if you have everything about your scene, the distance, the water, optical properties of the water, the BRDF of the objects, then you simulate an underwater scene. It's a forward model. This model was then refined by Jules Jaffe in the early 90s. So we still refer to this as the McGlamery-Jaffe model, commonly used forward model. And here is the key. In 1999, Sri Nayar and Srinivas Narasimhan published a seminal paper called Computer Vision in Bad Weather. And what they did there is they took the radiative transfer equation, they simplified it for the conditions of the atmosphere, remember, wavelength independent attenuation, and they simplified it for the RGB color space. And for the next 20-something years, we have been using that image formation model for underwater images. And only in 2018, we finally derived the first physics-based image formation model for the ocean. Here we call it the revised underwater image formation model, but if you consider the original one was for the atmosphere, it's not really revised, it's the first model for the ocean. This model has more parameters, it is more difficult to solve, but it shows very clearly that we couldn't have solved this problem without all those parameters, and the atmospheric model was not enough for the ocean conditions. So I will quickly remind you this former equation where I ask you to remember that the beta in the two terms was the same. The revised model, or the ocean-specific model, is the one on the bottom, which looks very similar, but notice that now the two coefficients are different. They are called the attenuation coefficient in the first term and the backscatter coefficient for the second term. And in parentheses, they have dependencies on different things. What they are is not important to my talk today. Just note that these coefficients are not equal to each other and they depend on different things. So the problem is a lot more complicated than we thought. To give you an idea of how complicated, when we were using the atmospheric image formation model, we thought that having one parameter for the entire scene for each color channel, so 3 parameters, was enough to do color correction for the whole image. Now we know we need a parameter for each pixel to do color correction, not one for the whole image, but for each pixel. So it is a very hard problem. And I want to show you briefly the power of this new or ocean-specific model. Here's an experiment I did in the Red Sea. I hung up a color chart on a line in the middle of the water, and I imaged this color chart from 8 meters on the left of the screen all the way to 30 centimeters. And as I got closer to it, I took more photos. Here you see the raw images. Note in the far distances from 8 meters to 7 to 6 to 5, that occluding layer of fog, that haze, is very obvious, right? There is a curtain of fog in front of the color chart. Now, using the color chart and the new equation we derived, I'm going to compute the parameters I need, and I'm going to remove that fog from the image. In the second row, you see every image without the fog. So I now calculated backscatter and I subtracted it. And you see that the colors are still attenuated. That's okay. We did not attempt to correct the colors, but that occluding layer of fog is gone. Now you see the furthest color chart with the same sharpness as you see the closest color chart. And next, I am going to use the patches again to compute the parameters I need to restore the colors. And that's what that looks like. Each color chart at each distance is compensated in a consistent way, and you don't see any of the three failure modes that I described earlier. So this is essentially what was holding us back from being able to do consistent, repeatable color reconstruction. But maybe you're thinking, excellent, you have a new equation, but it's more complicated, it's more difficult to solve. And here in this pretty calibrated experiment, you had a color chart. In real life, we don't have color charts. It's not possible to drop it, image it, and then remove it. What do we do when you don't have a color chart in the scene? And the answer to that is the Sea-thru algorithm. I'm gonna skip ahead a bit. Sea-thru is essentially a method that is the first method that uses the new image formation model, and it cleverly estimates those many parameters that the new equation requires. So it's not an artificial intelligence method. There is no training, there was no learning. It's a physics-based method in that it tries to compute the parameters, it tries to plug them into that equation, and it tries to remove them. In other words, remove the effects of water from the equation. I can't stress enough that it is not an AI algorithm. It's a physics-based algorithm, and it doesn't need to know anything about the scene, no color chart, not the water properties, nothing. So we are sort of short on time. We start a bit late. Let's look at the results before we talk about how it works. Here's a scene from the Red Sea. And it's the same scene now with the degrading effects of the water removed. And pay attention to the far pixels. They are corrected the same way as the near pixels. Here's my all-time favorite scene from Papua New Guinea. When we remove the degrading effects of the water, the chromatic richness is just incredible. And this is what makes me think every time, why are these colors there? If they are going to be invisible behind the color of the ocean water, all made blue, some shade of blue, why does anything in the water have color? Here's a scene actually not far from you guys. This is north of Boston, Cape Ann. I don't know if there are divers. This is the Chester Poling wreck. And of course, the very productive waters around Boston are green. So behind that green is the shipwreck that we see. Here's a scene from Indonesia. It's a very murky shipping channel. But when we remove the effects of the water, it is like a garden, just a colorful garden. because the algorithm does not need to know anything about the water, any image taken in natural daylight can be reconstructed using see-through. Here's an image that a follower, a social media follower sent me. It's an outdoor pool in California. His daughter is actually in this synchronized swimming team. And here is what it looks like without the water between the camera and the swimmers. We can see to the skin tone of the swimmers. Two most common questions I get: does it work for freshwater? Does it work for video? The answer to both is yes. This is a lake from Zambia. The researchers here are tracking individual fish to be able to understand their behavior. And they're training a machine learning algorithm to track the fish. And when they train the algorithm on the original images, annotations take a long time, the learning takes a long time, but they can significantly speed that up if they standardize the light in their imagery before training their machine learning algorithms. I realize I've gone a bit fast, but we did start rather late. And I just want to finish by showing you that there is nothing that stops us from applying see-through or the new ocean-specific image formation model to the atmosphere. Because if you think back, the atmosphere is a simplified case for the ocean when those two coefficients are equal to each other. And unfortunately, you will remember the terrible wildfires earlier this year or late 2020. And everybody woke up in California one morning with the sky looking like Mars. Well, what was happening was the ash from the fires was spewing into the atmosphere, and ash is an absorbing aerosol. So the color of the sky was no longer white, but it became yellow or orange based on that absorption. In other words, what happens in the ocean on any given day, on an ordinary day, happened in California one time and created great panic. So that's the gist of the new equation and the see-through algorithm. Essentially, I'm at the end of my talk. I just want to show you a glimpse into the future, because I didn't get into details so much, but this is not yet a real-time algorithm. And obviously, there's a lot of benefit for being able to see the true colors in the water when you are in the water, and also right after your dive without having to wait too long. Well, the key to making that work is being able to acquire distance real time, because the color correction part is just a matter of seconds, but the distance estimation is the problem. This year, I got a large grant to develop a LiDAR integrated RGB camera that hopefully will be affordable for research labs, and we will be able to do this mapping and color correction real time in a number of years. So there's early progress there, but it'll still take a few years. Here is a real-time algorithm I'm working on that essentially improves visibility and does color correction without needing a distance map, without needing any distance information. It's not as beautiful as see-through, but it is real-time, which has some advantages. So that's something in the works. In the beginning, I showed you examples from camouflage, which are very dear to my heart. See-through also opens up the possibility to look at classical problems like camouflage and visual ecology with a new lens. If you just look at the red arrow in both images, there's a cuttlefish there right in the center trying to camouflage. Which image do you think, in which habitat, which light environment, is it easier to camouflage? When light is monochromatic and there is no more color contrast and everything looks the same, or when light is broadband and things have color and you have color contrast. So potentially one reason why these animals did not evolve color vision is because they live in light limited monochromatic environments. I don't know, but that's something I'm very excited to explore. That being said, I am happy to announce that I'm starting my own lab later this year, and I am hiring interns, masters, PhDs, postdocs, anybody who's interested in understanding why there are all these colors on the bentos and what do they tell us. So if you're interested, if you know someone interested, if you want to collaborate with your own research, please don't hesitate to reach out to me. Nicole and Coral both have my email, and I would be more than happy to see how our paths can cross. So that actually, with 5 minutes late, that brings me to the end of my talk, and I would love to take your questions now. Thank you.
Thank you everyone for sticking around. If you need to go, then thank you so much. But if you want, oh, my camera is still off. If you want to stick around and ask some questions, then we're still here. Just for a little bit longer. You may write questions in the chat, or you unmute yourself, turn the camera on and speak.
I guess it was very clear then.
Yeah.
I was going to say, Derya, you did such a great job explaining everything. It was a very interesting talk.
Thank you. Happy to hear that, because there's so many different concepts at different disciplines that it's always hard to get it just right. If that's the case, I'm very happy. Thank you.
Yeah. Yeah.
A couple people are writing in the chat, and
Let's see.
So wonderful presentation, really interesting. We have a question from Tracy Mandel asking, can any of these be applied
from above the ocean surface, e.g. from a boat?
Yes, fantastic question, Tracy. Thank you. Can any of these be applied from above the ocean from a boat? The answer is yes, with some limitations. Limitations being, how far away are you? Maybe are you on a drone? Are you on a satellite? And how choppy the sea surface is. If it's a flat day, a calm day, you could have, and the water has reasonably good visibility, you can have very good visibility into the water column. If it's a choppy day, forget it. If it's a calm day but turbid water, you can have very little visibility. So it all depends, but yes, there is definitely some application there.
Okay, another question from Hillary Kate Vons. So cool, thank you, Derya. Do you foresee licensing your technology to companies like GoPro?
That's a very good question. We actually did have some talks with GoPro. That was before the pandemic began, and with the pandemic, I believe everybody's finance situation changed, and we paused there. So certainly, and I briefly mentioned Tali, my former postdoc advisor at Haifa. She's actually in charge of that, and she will be commercializing the algorithm and bringing it to the market. So hopefully this will be a tool that everybody, recreational, scientific, whatever, will be able to access.
Okay, Diane Foster says, Derya, that was a terrific talk. I'm wondering how well the algorithm works when the attenuation might change with depth, e.g. When there is sediment suspension near the bed, but not away from the bed where the camera is.
Excellent question. So Diane asks how, when attenuation gets worse, for example, you have clear water, but you're near the bottom and sand gets kicked up because propeller or diver fin, whatever, that will always be there. This algorithm will not remove the stuff that is actually physically hanging in the water column. So the quality of the result, the corrected result, will eventually depend on the input quality of the input image. So essentially that, Diane, that stuff, the sediment that's there, that goes in the image, that stays in the image. Okay. Hopefully there will be other methods to deal with it.
Yeah. Valmeet says that was terrific and fascinating.
Thank you.
Loud here, so I won't unmute. So he won't unmute.
Thank you.
Tracy, thank you, and says fascinating talk. Tamer Nada Thanks a lot. It was a great presentation. Good luck with your research. Looking forward for these real-time algorithm cameras.
Thank you.
Absolutely. Yuri has a question. Why turtle has UV receptors? It does not propagate underwater. Not all marine creatures see mono. Manta shrimp has 17 ones.
Excellent. So Yuri, of course, being an optics and light person, he brought up excellent points. Why do turtles have UV receptors? I can only speculate based on what we think, because they come on land to lay eggs, which generally happens anytime in the early afternoon to sunset, throughout the night to sunrise. There might be a need for UV there. Also, when turtles hatch, they have to find their way to sea. So they hatch, and in a panic, they have to go to the sea. Potentially, the hatchlings use it to locate to sea. It's known that it's a visual activity, but I'm not sure it's directly linked to UV, but maybe there's a role there. And also Yuri brings up a great point about the mantis shrimp. Mantis shrimp, this really aggressive, passive-aggressive animal that lives in a hole that he digs up himself and basically spends the entire time in the hole, has 17 channels of vision. And what's he doing with that? Not so clear, but it has it. Octopus, for example, are monochromats, which we think they are colorblind, but they have polarization vision. What are they doing with their polarization vision? We don't know. The sea is full of mysterious visual systems, and we very poorly understand them.
Okay. Yeah, the young Foster says thank you, and oh, Massimo says awesome talk. Thank you as well.
Thank you.
I think this is it. I hope I didn't miss anyone. Yeah, Andrew Armstrong, Juliet Guinea, everyone says great talk.
Thank you, guys. I hope I could explain the difficulty of the problem.
Okay, one last question from Yuri. Does your algorithm require
knowing depth? No. Again, that's a fantastic point that Yuri brings up. So if you just think back to the octopus simulate the scene with the diver and the octopus I showed, what affects color loss the most, the attenuation the most, is the distance directly between the diver and the octopus, because that has to be pixel-wise corrected. The change of color from depth actually can be corrected globally with just one number for the whole image. So the algorithm does not need to know depth. It sort of uses white balancing tricks like gray world assumption or rednecks to compensate for that without knowing depth. If you knew depth, would that help you? It would only help you if you also know the optical properties of the water and if you also knew the camera sensor. So just depth alone would not have helped. That's why we don't try to estimate it.
Okay, one last question from Massimo. Can we try it on stereo photos of the seafloor?
Yes, absolutely. So stereo gives you distance. When it's calibrated, when we have distance, we can certainly try it. Absolutely, yes.
Okay.
Absolutely.
So I think with this, we're done. Thank you so much, Darya. Okay, Yuri has more questions.
I am happy to stay on, so I'm in no rush. Happy to take all of them.
Balancing is known to distort colors. Your algorithm has anything with it, with balancing?
So the white balancing step, Yuri, is at the very end after the pixel-wise color attenuation is compensated. At that point, it doesn't distort, because at that point, you have the equivalent of a scene on land, and it's just like white balancing on land, like you change the yellow light in your office to white light. If you white balance without compensating for the distance between the camera and the scene, then it will distort colors. That's actually a very common problem, a very common mistake.
Thomas says, great work, excited to learn more about what we can do with see-through. Val says, you might have just explained this, but does it matter if you take images looking downward into deeper depths versus taking an image over the same range but at constant depth? Yeah, you just answered yours question.
I did, but it's a good point. Those eventually become equivalent, either deeper depth or shallow depth and looking further distance. So they would have to be compensated with the same aggressive correction rather than assuming one is simpler than the other. Yeah.
Okay. So I think that with that, we will finish. Thank you so much, Derya. Thank you for everyone for joining us and sticking around and for all of your interesting and good questions.
My pleasure. Thank you for your invitation, Coral and Nicole. It was nice to see you in person as well. See you. So have a good afternoon, everybody. Bye.